MEM School of Engineering, Department of Mechatronics Engineering, online classes, subject robot, machine, and vision systems. Myself, Sarvan, Assistant Professor, Mechatronics. So today we are going to see about the unit number 5. So that is digital image fundamentals of a machine vision system. Okay. So already we know that robot doesn't have any ears, any eyes. Okay, we need to give the eyes and ears through the sensor activities. So like that, one of the vision activities are digital image processing. So using cameras, we can detect the image of the object that was manufactured. So using the image processing, we can identify the defects in the products. So like that, we can analyze in the digital image process. So last class we discussed about in chapter 1 we discussed that is what are the components used in the digital image processing tools like that camera, lighting, then computer and software. So like that we discussed. Okay. So in chapter 2, we are going to see about the basic digital image fundamentals. So what is a digital image? So then what are the fundamentals of digital image like that we are going to discuss. So these are the basic digital image fundamentals, that is elements of visual perception, image sensing and acquisition, sampling and quantization. So relationship between pixels. The human visual system, a true measure of image processing quality is how well the image appears to the observer. The HPS is very complex and is not understood well in a complete sense. However, many of its properties can be identified and used to our advantage. So this is the structure of human eye. So we are like this. We are like this human eye. We are going to fix the camera for identify the objects. So image formation in the eye. So same concept we are going to recreate in the images. That is, lens is flexible and its refraction is controlled by its thickness. The thickness is controlled by the tension of muscles. Focus on distant objects. So lens is relatively flattened. Refractive power is minimum. So focus on near object. Lens is thicker. Refractive power is maximum. So perception takes place by excitation of receptors which transform radiant energy into electrical impulse that are decoded by the brain. So this is a basic brightness and intensity of the image, that is how to varying like that we are going to see. So the dynamic range of light intensity to which eye can adapt is enormous. So brightness is a logarithmic function of light intensity. So HVS cannot operate over the entire range simultaneously. It is accomplished large variation due to the brightness adaptation. So relationship between brightness and intensity is not a simple function. So this is an example for brightness and intensity. Okay. So next one is image sensing and acquisition concept. If a sensor can be developed that is capable of detecting energy radiated, so by a band of the EM spectrum, we can image events in that band. So image is generated by energy of the illumination source reflected or transmitted through the objects, that is X-ray. A sensor detects the energy and converts it to electrical signals. So sensor should have a material that is responsive to the particular type of energy being detected. So this is a simple image formation. So the image magnitude depend on the amount of source illumination incident on this scene, that is I of x comma y. So the amount of illumination reflected by the object in the scene r of x comma y. That is function of x comma y is equal to I of x comma y into r of x comma y. Sampling and quantization. So computer processing. So image f of x comma y must be digitized both spatially and in amplitude. So digitalization in spatial coordinates called sampling. So digitalization in amplitude called quantization. Okay. If you are converting with the spatial coordinates when it is sampling, if you are converting with the amplitude means that is quantization. That is image of f of I comma j with respect to the n into m. So what should be the values of n and m and the number of gray levels g? So normally n is equal to 2 power n, m is equal to 2 power m, g is equal to 2 power k. Depending on the number of pixels. Okay. So this is an example of sample quantization coordinate system. That is coordinate convention used in this book to represent the digital images. So number of bits required to store the images, that is n into m into k. The more of the values of nmg, the better approximation of continuous images. Storage and processing requirements increases well. So this is the effect of reducing spatial resolution. So first we see first image is 1024 into 1024. So second image again sampled by the 8-bit, that is 3232. So then the number of allowable condition gave up to 256. So there is the spatial resolution of the given images with respect to the reduction of uh, number of pixels. So this is the reduction of spatial resolution. Yeah, same concept we are using. So there is 1024 from 1024 to 32. So this is the effect of reducing the gray level. Okay, you can see the different variations in the reducing the gray levels. So this is also reducing the gray levels. So zooming and shrinking. Zooming means increasing the resolution of an image. Shrinkage is a decrease the resolution of an image. So 6 pixels is converted to the 36 or 30 pixels. 30 pixels, that is called zooming. So 30 pixels converted into 6 or 8. So like that, that is shrinkage of images. So pixel replication. So interpolated pixel in the enlarged image is set to the gray level of its nearest pixel in the original image. So bilinear interpolation, interpolated pixel in the enlarged image is set to the average its 4 nearest pixels in the original image. So this is the example of zooming. Shrinkage. So by an integer number can be done by deleting some of the rows and column of the image. So shrinkage by a nonlinear factor, integer factor can be done as the inverse of zooming. So this is the relationship between the pixels. So relationship between the pixels called neighbors, adjacent the path, connectivity, region, boundary, and distance. Okay, basic relationship between the pixels. A pixel P at a coordinate x comma y has 4 horizontal and vertical neighbors. That is n of p is equal to x plus 1 comma y, x minus 1, 1 comma y, x comma y plus 1, x comma y minus 1. Okay, this is the basic vertical, horizontal and vertical neighbors. So same as 4 diagonal neighbors and 8 point neighbors P. Okay, so these are the basic fundamental processing of the digital image process. Okay, so the sampling, quantization, then zooming and shrinking. These are the gray level variations. So these are the basic operations of the digital image processing. Okay, so remaining we will see in the next class.